Okay, just a reminder that at 3 o'clock today, there is a sciencey person coming to speak in the library, Davis Sobel. We talked about her as an author, and she'll talk about her experiences as a female science writer. We don't get a lot of math science speakers here at GCC, so this promises to be a good one. 3 o'clock at the library. Next thing. Okay, we'll do both of these in a second. All right, so the next thing, you're kidding, right? All right, the next thing is the calendar. So you are currently working on project number 7. It is called DEUCE. Today we talk about the integral test, and in general, this is our first of a number of days about convergence of different series. And our next class, you can see, is actually not until a full week from now. So just a reminder that this coming Friday is a professional development day. So the employees come in, but the students don't have any classes. All right, so no classes on Friday. And then Monday coming up is Patriots Day, and there are no classes on that day either. So we won't be back in this room together until Wednesday, a week from now. Questions on the calendar? There's no extra homework. There's just the one homework assignment. No. There's no class, no homework. So just a regular homework assignment due 1 week from today. Okay. All right, so the integral test. Before we jump in with the integral test, let me just give you a hint about the project. So this is project 7. Again, it's called DEUCE. There is a hint on YouTube. If you go check out one of my videos from a little while ago and you type in exactly the following phrase, 2022015 April 19, with no spaces. 2022013 April 19. Yeah. So if you type that thing in, first YouTube will say, are you sure you didn't want spaces? And it'll show you a bunch of random videos with spaces in the title. And you say, no, really, I meant this. And you click on the thing that says, I really meant this. And then my video will be the only one that pops up. And the first 5 minutes or so is me going through a problem that will help you with understanding a little bit about probability. It's a related but different problem than the one on the project, okay? It's supposed to help you with the whole project, but it's really just about the probability. There's no calculus in this in the hint. It's really just to fill in. So if you have any gaps, so if you don't understand the basic probability questions on the first page of this project, you go to this video and it will help you there, okay? It's not required. This isn't like that Gamma project hint where you really, like, I can't expect anybody to come up with this without a push. Plenty of you will be able to do this project without watching that video. But if you get stuck because you just don't understand what's going on with the probabilities on the first page, you check out the first few minutes of that video, okay? You're welcome. All right, and then the other thing I wanted to take a quick look at is just a few pages prior to this one. And I feel like I kind of fumbled around on that finite geometric series formula, this guy here. Remember how I talked about there's just this confusion between like which term are you looking at and what's the power up there, and it's typically off by 1. Okay, so new way to think about this one. I'm just going to say this, that the power, I'm on page 11 if you want to go back and update our formula here. This power right here is the number of terms. Nothing more and nothing less. So I don't get distracted by like what's the subscript, and because like if you start the thing at S0 versus starting it at S1, then you got to memorize 2 different formulas. It's just the number of terms. Yes, every term that you see. I don't care what you call them. It's just how many terms. So I'll just put up a quick example here. Summation of k equals 2 to 5 of 1/2 to the k. Okay, so let's just write out all of these terms. There's very few. Okay, so we start by plugging in k equals 2. We get 1/2 squared, which is 1/4, plus sigma. K equals 3 now, so 1/2 cubed is 1/2 cubed is 1/8, plus then now we're up to 4 for the power, 1/16. and now we're up to 5 for the power. That's 1 over 32, and then we stop because it said stop at 5. All right? So what I'm telling you is that if you want to add these guys up, this is a geometric series because every term is the same multiple of the previous term. Then we can use our fancy formula up there. So let's use our fancy formula. A is the first term. What's that? 11. A is the first term. What is the first term in this series? It is 1/4 times 1 minus x to the n. 1 minus x is the magic ratio. What is it in this case? It's a half. Raised to the n. It looks kind of like it's a 5, but it starts at 2. So what are we doing? It's just how many terms? How many terms? 4. Right? So don't get distracted by like starting and ending and powers. It's just the number of terms. So this is to the 4. And then it's divided by the 1 minus x. 1 minus a half. And if you crunch that through, you'll get the right answer. It's silly to use that formula on this easy series, but I just wanted to highlight the power is the number of terms. Questions on that one? That's going to give you the sum of those 4 terms. This series right here could care less that we're starting at 2 and ending at 5. I'm just saying you are adding that stuff up. It's kind of arbitrary that I'm saying I'm calling this first term the one that goes with k equals 2. You could rename it and say, well, that's really s sub 0, or that's really s sub 1. And that's why I don't want to get distracted by what we call it, because we could call it anything. What I'm saying is that regardless of what you call it, this is the formula to add up those 4 terms. Other questions on this one? Power is the number of terms. Yeah. Okay, so moving on back to page 19. And we are here. Okay, so let's go to Rob, daily summary. Okay, so let me highlight at this moment that the fact that we have that formula from last class, remember the a over 1 minus x to add up an infinite geometric series, that is quite unusual for us to actually know what something adds up to in the forever. At this point, and for the next couple of weeks, the only answers that we're going to be giving about series are, yes, it converges because, no, it diverges because. And if it converges, we're not going to have any idea what it converges to. It is very rare that we'll actually know, oh yeah, this thing approaches 2, right? Like Alex's series from last class. Yeah, if you go forever, it adds up to 2. So that is quite unusual to know what it adds up to. So for the next few weeks, almost all of our answers are going to be, yes, it converges because, no, it diverges because. All right? If it's a geometric series, we can find the exact sum because we have a formula. But almost all of the series we're going to be looking at in the next few weeks are not geometric. Yeah. Okay, so let's try number 1 here. Forget the directions, and in fact, I want to change this guy right here. So we're going to change this to make it more complicated. Let's try this. 2 minus 3n squared over 5n squared. That's a little bit more complicated. Okay, so let's talk about this guy right here. So the first thing I want to do is write out, it says the first 5 terms. We might just stop at 3 or something, but let's write the first few anyway. So we begin with what value of n? 1. So we plug n equals 1 everywhere. What do we get? Rich says minus 1/5. Agree? Okay. Plus, now we're going to plug in n equals 2 everywhere. I'm going to leave it unreduced first, but I think it's that, right? We get a 10 over 20. Is that okay? Okay, let's do one more term. So what are we plugging in now? 3 for n? Okay, let's see, that's 27 minus 25. Negative 25 over 45. Okay, and it goes on forever. So we'll just say plus dot dot dot. So the question is, how does it converge if we add all of these guys up forever? And is this a geometric series? Is there something that you can multiply consistently by to get from one fraction to the next? Let's see, a fifth to get to a half. I guess that's multiplying by 5 halves. What do you want to do? Yeah, let's figure out what these terms are doing, and then we'll think about what the series is doing. And so I think I heard Levi say it converged. The terms converged to what number? How'd you get 3 over 5, Levi? So Alex is talking about polynomial over polynomial, and we're imagining plugging in really big numbers for n. Ultimately, that's what we care about, is what happens way down the line, not what happens here in the beginning. And we see that it's the same power on top and bottom, n squared, n squared. The 2 is irrelevant, right, relative to these enormous numbers we're plugging in. So the terms converge to -3/5. These guys get closer and closer to -3/5. So in essence, we are adding up forever a bunch of -3/5. What happens to that when you add it up forever? It goes to minus infinity, right? If you just keep adding -3/5, you're going to go to minus infinity. So does that series converge or diverge? It diverges. If it doesn't go towards a single finite number, the series diverges. So yeah, so let's say this. The limit as n goes to infinity of the terms, that is just the sequence itself, converges to what number? To -3/5. And the series, therefore, is essentially adding infinitely many of those. And so the series diverges. Is there a difference in divergence? They both diverge. Okay, so an opportunity to be really confused here because we have two different kinds of things that either converge or diverge. The sequence itself, just a list of numbers, converges, but the series diverges. And it's really important that we have this distinction. Okay, let's take a look at part B. Sum of 1 over n. N goes from 1 to infinity. Let's list the first few terms of this. We begin by plugging in n equals 1. We get 1 over 1, that's fine, plus 1/2 plus 1/3. We'll do one more, plus 1/4, plus dot dot dot. So what happens to the terms of this series when n goes to infinity? These terms go to 0, yes? Those are getting smaller and smaller and smaller. That means nothing. It's really tempting to say, oh, as long as the terms go to 0, then the series will add up to some finite number. That is not true. Could be true, but it's not true. So the fact that the terms here go to 0, it's actually like the worst news, but it's the most common news. It's news that we have to do more work. That's what it means. The terms themselves converge to what number? 0. But the series where we're adding these things forever, I don't know. No. They will change. Okay, so part B, we don't know yet. We don't know what the answer is. It might converge, it might diverge. Part C, 1 over n squared. Let's write out for the first few of these guys. 1 over 1 plus, what's the next one? Right, because that's plugging in n equals 2 and then squaring it, plus 2 more. 1 over 9, 1 over 16. And so for this one, limit as n goes to infinity of the sequence is also 0, and as Elias says, it goes to 0 faster, right, than the previous list. They're both going to 0, so it feels like it hardly matters. But if we had to weigh in, we would say, yeah, this one goes to 0 faster. No, that's so here's the surprise. This red series converges. If you add this up, it goes to a finite number. In fact, this is one of the few where we can actually tell what, well, we can't, but a mathematical genius that lived a few hundred years ago could tell what that series converges to. The red thing converges to a finite number. I will show you what that is in a couple minutes. The pink or purple series goes to infinity. If you keep adding those things in purple, it will exceed any finite number. It will get past 100. It will get past a million. It will get past a Google. Whereas that red thing converges to something like 1.5. All right, so we're going to talk about the cutoff. But I'm just putting out here that there's a big surprise. And just because the terms go to 0, you can still have 2 different answers for this series, okay? We agreed up here that these terms going to -3/5 is the end of the game, right? If you just keep adding -3/5, clearly you are not going to hone in on a single number. You're going to go to minus infinity. But most of our series are going to have terms that go to 0, and we're going to develop a whole theory about how to decide which are the ones that converge and which are the ones that diverge. Okay, part D, I want to change this guy a little bit too. Let's cross this off and make it 7 times 2/3 to the n minus 1. So let's list out the first few terms here. When we plug in n equals 1, 7, plus, now we do n equals 2, 14/3, and now we're doing n equals 3. Right here, is that right? Yes? All right, one more. It's a little bit tough to do all these in your head, but I think we could do one more. So n equals 4. Yeah, so n equals 4, which means the power up here is really a 3. So I'm doing 2 cubed, which is 8, times the 7 out there, 56. And then I'm doing 3 cubed down here, so that's a 27. Okay. So what kind of a series? Well, first of all, let's go back to our question from before. What's happening with these terms here? Limit as n goes to infinity, 7 times 2/3 to the n minus 1. Are they getting smaller? It looks like they're getting a little bit smaller. It's really, I mean, you really can't tell anything from the first 5 terms, right? I mean, it's really the forever part that we care about. So just look back here. 2/3, you keep multiplying by 2/3. That's what this says. So what happens in the limit? It goes to 0. Yeah? Right. The 7 might make it like, might pull it up a little bit in the beginning, but eventually you keep taking enough 2/3 and it's going to shrink down to a little wisp of nothing. Okay, so the thing goes to 0. That's bad news for us. It doesn't tell us anything about the series. It might converge, it might diverge, but what kind of a series is that? It has a name. That is a geometric series, right? And we just got to start recognizing them. What's the common multiplier here? Is 2/3. And in fact, maybe we should have recognized that from the beginning, because this is saying keep multiplying by higher and higher powers of 2/3. So if it's a geometric series, we know everything there is to know about it, provided we can recognize it's a geometric series. So this guy right up above is geometric. I think we said the ratio is x. What is the common ratio in this case? 2/3. What's our magic range for convergent geometric series? Yeah, as long as your ratio, your multiplier is between -1 and 1, then the series converges. So since the 2/3 is between, we know that the series, and I'm just going to write it out, I'm really not a fan of the word it in math class. It converges. I'm going to write down in a big red marker. What is it? Now, what did I do? Yes. What is it? So this series right here converges. And in this case, again, like hardly ever can we actually say what it converges to, but geometric is like the only one that we can. So A, first term, 7 divided by 1 minus the x, 2/3. So what is that? Is that 21? 21. So if you add those guys forever, which is 21. Yes. We have, yes, we have a negative result that we can look for. We're going to have you read that in just a second. Levi.
So you can tell what it converges to even though the exponent in the series is -1.
Yeah. Yeah, because the series doesn't care that we've called it n-1 instead of n. Like n is just convenient for us.
It starts off a little bit different.
Well, the question is, what can you multiply this guy by to get? Right. Okay, so we're going to have Elia read number 2 for us. Okay, which was the one that had terms not going to 0? It was A. The terms are going to -3/5. You add infinitely many of those, you're going to blow up or go down to -infinity. So this series diverges. All we're going to do is add a tiny phrase here. What's the name of this test that we just named? By the nth term test for divergence. Or divergence. Nth term test. No, because you're going to be so excited the one time you get to use it that you'll be happy to write it out. Because most of the time the terms are going to go to 0 and that doesn't tell us anything useful, right? But the very first thing to look for, hey, maybe this is the one time we get lucky and the terms don't go to 0 and the answer is obviously diverge. That's the nth term test for divergence. All right, so moving on. We're going to take a look at this guy right here. We talked about it up above, but 1 plus a half plus a third forever. So it actually has a name. It is a very famous series. It is called the Harmonic Series, which is a musical word. So named, and I don't quite understand the sentence, but maybe the musicians in the room will, because the overtones of a vibrating string have wavelengths that are a half of the fundamental wavelength of the string, or a third of the fundamental, or a quarter. So like if you're playing a guitar and you put your finger like halfway along the length of the string, you get like a certain thing called an overtone. And if you put your finger at the 1/3 mark, you get the next overtone, and the 1/4 mark. Awesome. All right, next page. Okay, so here's the surprising part. Despite the fact that the terms of the harmonic series, that's the one we just looked at, the terms go to 0, the series itself still diverges. Meaning if you add them up, it goes to infinity, which is quite surprising. It turns out to be true. So let's move on to number 5. We'll go to Dean. Sam. Number 5 now. We just read that one. Next part. All right, here we go. So we're going to first consider this integral of 1 over x from 1 to infinity. There's the picture. You don't need to shade this in, but I will for just a second. But the integral that we were talking about is thinking about this area, right? Forever. We know whether this is finite or infinite from way back? Anybody remember? Yeah, we're right at the cutoff. What's that? 1 or below, it does what? It diverged, right. So this guy right here is the cutoff. If I had changed this power to a squared, then all of a sudden it would be a finite area, but 1 is the cutoff, and anything below 1 is on the bad side, it diverges. And so we saw already that that is an infinite area there in blue. So we know this to be true. So now what we're going to do is we're going to approximate that thing. Even though we know it's infinity, we're going to approximate it by drawing in left rectangles. So on the interval from 1 to 2, we're going to use the left-hand endpoint to determine the height. So does everybody buy that's the very first left-hand rectangle? Between 1 and 2, you choose the left-hand endpoint. And then between 2 and 3, we choose the left-hand endpoint. That's pretty poor. So we choose the left-hand endpoint, and we'll do one more over there. There? Now let's write out the areas of these first few rectangles. What's the area of that first rectangle? This one. Okay, easy enough. Just count boxes. Plus. Why is it a half? Yeah, because it's 1 over x, and that x is 2. So the height of this little second box here is a half, and the width is 1, so that's has an area of a half. The next one has an area of 1/3, and then plus dot, dot, dot. Now, this green thing right here has a name. What's it called? That is the harmonic series. 1 plus a half plus a third forever is the harmonic series. Is that green thing more or less than the blue area? It is more. And is that blue area finite or infinite? Infinite. So green must be infinite. It's bigger than the already infinite blue. Yeah? Yeah. Okay. So we don't need to write a lot down. We're just going to, we'll have a big conclusion in a second with the integral test. But let's move on. Everybody has what they need. Let's move on to number 6. And we're going to look at the sum of 1 over n squared and see if we can figure out whether or not it converges by comparing it to a known integral. The thing that made the previous work is that we already knew that integral was infinite. And so let's look at this new integral here, integral from 1 to infinity of 1 over x squared. So again, you don't need to draw it. I'll do it in blue again. But that integral is concerned with this area here. Notice how much faster this curve gets to the x-axis. Never gets there, but that's sure a whole lot tinier than the area in the previous picture. And we already know whether that area forever is finite or infinite. Which is it? This is finite, because that squared is bigger than 1. 1 is the cutoff, and if you are bigger than the cutoff, you are finite. So we know the blue area is finite. What we're going to do is we're going to approximate that blue area, approximate this integral, by drawing in some right rectangles. So between 1 and 2, which point do I pick to determine? All right, so we're going to pick 2, go up to there, and we're going to go there. And then we're going to draw one more of these rectangles. Between 2 and 3, which point do we pick? 3. And I said we're only going to draw one more because I can't even draw the thing at 4. It's so, right? Sorry. So close to the axis. I can't draw it. Let's write down some areas here. The height of that first purple rectangle is a quarter, yeah? So that's a quarter, plus the height of the next one is 1/9. I didn't draw it, but the next one would be 1/16. Okay, yeah, there's a little funny thing happening here. What's the first term in this guy? Is 1, and the next term is our quarter, right? 2 squared, and then a 9th, and then a 16th. Okay, so we're missing the 1, but aside from that, they match up perfectly, right? Okay, we know that blue forever is what? Finite or infinite? Finite. So purple forever is less than that finite thing. So purple must be finite. So if you add all these purple things and it's finite, and then we throw in the missing 1, still finite, right? No problems. Okay, it's a surprise. The 1 over n goes to infinity, but 1 over n squared converges. It's finite. Okay, so the important thing here isn't that you have to know, okay, in this case you got to draw right rectangles, and in this case you have to draw left rectangles. The important thing is that as long as you do the right integral, then the integral and the series behave the same. So our our first series was the harmonic one. And we looked at the integral of 1 over x, just like 1 over n. And they both did the same thing, right? We saw that the harmonic was infinite because the integral was infinite. And then coming down here, comparing the red series, 1 over n squared, to this purple integral, 1 over x squared, they both behave the same. We knew that the purple thing converged. We proved, therefore, that the red series converges. So it's just that they do the same, and you don't even need to pay attention to, oh, I'm using left rectangles or right rectangles. We should now be convinced that they do the same. And that's what the integral test says. No, they have to behave the same, as long as we have certain conditions that we haven't highlighted, but we'll talk about. Okay, so real quick, sum of 1 over n squared, this purple thing, well, I guess the red thing up here, it converges. We have no earthly idea what it converges to normally, but like I said, some really smart person, his name was Leonard Euler, he was a Swiss mathematician back in the 1700s, he said, oh, I know what it converges to, pi squared over 6. Of course. Of course. So we're not going to get into how, but I made a little spreadsheet in Excel. We're trying to look at 1 over n squared. So this first column is just 1, 2, 3, 4, 5. The second column, we'll scroll to the bottom in a second. Second column is the squares of the first column. Yeah? Next column is 1 over the previous column. So what is this, 0.25? That's 1 over the quarter, and then this 0.1 is 1 over the 9, okay? And then we're doing partial sums. The first partial sum is just this guy. So here are the terms. That's 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, all right? So here we're just adding up partial sums. The first term is just this guy. What is this? That's the sum of the first 2 terms. What is this? That's the sum of the first 3 terms, okay? So we are looking at this list right here, and I'll scroll down real quick. Whoa, what happened? Let's go there. So we're trying to figure out what this guy goes to, so I'm gonna scroll down. All right, so that's 100,000 terms. So 1.6449, it sure looks like it's honing in on something, right? You can see how slowly it's changing. So that's what it converges to. Euler said, oh, I know that number, that's pi squared over 6. So to convince you, what I did is I took the square root of 6 times the previous column. So what we're saying is that the sum is pi squared over 6. So if I wanted to solve that equation for pi, what would I do first? Multiply by 6 and then square root it. So 6 there and then square root. And so if we're right, then if I take the square root of 6 times the sum, we should get approximations for pi. So let's scroll down again to the bottom here. So how many digits do you guys know? So 3.1415, what should the next digit be? Should be 9. But we're getting there. So we're at 8.3 right now. I'll show you when we were at 8.2 there. So 8.2 is, yeah, so it took about 10,000 terms to go from this 8.2 to 8.3. But eventually we will get to 9, which is the next digit in pi, and it will get past that and hone in. Like I said, he's a really smart guy. Okay, the integral test. Here's the idea. We've got some formula for the nth term. It could be, for example, 1 over n, or it could be, for example, 1 over n squared. If that function satisfies a couple of conditions, these are important. The function needs to be decreasing and always positive from some point on. Then the integral test applies, and what it says is that if the integral converges, then so does the series, and if the integral diverges, then so does the series. They behave the same. That's our shorthand. We cannot use this on sine of 1 over n. So let's talk about the different conditions here. Suppose that my graph was something like sine. If we look at right-hand rectangles, are they always above? Are they always below? Oh. So what about those two functions made it so that we could say, oh yeah, they're always above or they're always below? The function itself was decreasing the whole time. That's what made it so that our rectangles were consistently above or consistently below. And we need stuff to be positive. I guess the same kind of thing. I mean, like, Yeah, because what do these terms have to go to for us to have any chance of converging? The terms themselves, what do they have to go to for the series? They have to go to 0, right? And so if you are decreasing, as soon as you get past the x-axis, you are not going to 0 anymore, right? So that's the positive part. So positive makes it so that maybe we're heading to 0. Then it won't be decreasing anymore. I mean, if you just focus on this part where it's increasing the whole time, then I think you could probably use this like a modified version of this integral test. But the integral test is very precise. Got to be decreasing and positive all the time. Okay, so activities begin on the next page. I don't think I'm making any changes. No, they look good. So jump in and I will walk around. You can do the same thing.